Hi, today I will show you first of all what the electric field of a certain charge distribution is, how fields transform, and how to argue with symmetry, certain things which should be true. Okay, first of all, say you have a shape distribution of charge like this, a nugget of charge you could say. Say that the electric field of it happens to look like this here in the picture. Okay, now intuitively, we know that, let's say this vector right here, let me lengthen it a little bit. This vector right here is longer, this one's shorter. Say this one's the shortest. Alright. Now, we know intuitively that if we rotate the shape, then the field also rotates with it. And it does so in the following fashion. Say I rotate it like this. Okay, then it looks like that. Notice basically that this means every field vector is rotated by the same amount that the shape is rotated. Okay, like so. Alright. Now knowing this, that this is how the field should transform, if you do a transformation to the actual transformation of space to the actual shape of the thing, which in this case is a rigid transformation or rotation, and well, this was slightly translated too, but anyhow, that it should be take this form. Okay. Now imagine you had imagine you had a sphere of charge. And it's that the thing is everywhere, the same, etc. So basically, another way to say this is that it's rotationally symmetric, right? And it's also symmetric about flips that cut the sphere in perfect halves. It could be planes oriented anywhere in space that just happen to cut the sphere in half. Okay. So now amongst the different things in particular, say I pick a point in the center of the sphere and I pick an axis of rotation through that center. Okay. Since this charge is symmetric about all those rotations and transformations I mentioned, right? In particular, with respect to rotation about this axis, right, the distribution stays the same. So therefore the electric field should also be the same. But we already mentioned before, right, that upon rotation, like up here, the field itself should rotate. So for example, if I had this vector right here, let's say this was, we don't know yet as of now how the vectors for the electric field of the sphere looks for this uniform charge distribution, but let's say for now that it looked like this, right? Well, according to the story up here, when I do the rotation like this about here, then it should end up like this. So in other words, this vector should also rotate. Like it's almost like if it were a rigid shape. So up here, it's almost like you had a rigid urchin and you just rotated the urchin. Here, the same story. You had a rigid urchin with a spike here, and you rotated, and now the spike is over here. Okay. So, but it turns out here's the thing in this case that we're going to argue, because again, we still don't know that the field looks like this or whatever it looks like. Okay. But we know that it should transform in this way after the rotation. But the other thing that we know is that since this distribution is symmetric, right, after you rotate the thing, it's exactly the same as it was in the beginning. So in other words, that vector field after you rotate it should be the same thing as it was before. So now we'll see how the electric field of this charge distribution looks like. And here we go. Take again the same charge distribution, right? Again, we took that axis, this particular axis that we had picked here, right through the center of the sphere. All right. Now, what does the electric field look like at a point here, for example? Well, if it looked like this, after you rotate it, it would look like this. So it wouldn't be the same as when it started, but the distribution is the same, so the field ought to be the same. If it looked like this after you rotate, now it looks like this. So again, the field is, what should be true is that it's the same before and after. So you notice then that the only way that the field could look is like this. Let me make it really dark here. Either pointing this way or pointing this way. Why? Because those are the only two vectors that you can have here for the field, where after the rotation they look the same before and after. So right away from just that symmetry argument, you can tell that if you have a uniform spherical charge distribution, then the electric field generated by that should either point away centrally from the sphere or towards the sphere. And of course, these would correspond to the cases where the charge is positive or the charge is negative. So there's your first symmetry argument. So now you know how with symmetry you can argue what the electric field of a spherical charge distribution should be.